So today we will continue with the chapter on current electricity, and this is the last session regarding current electricity, and we have already completed with the topics under current electricity, that is Kirchhoff's laws, Wheatstone's bridge, meter bridge, potentiometer, galvanometer and ammeter also we completed in the uh, previous video, and today we will explain in detail about the voltmeter. So we will go to the next slide, how you can convert a galvanometer into a voltmeter. Now all of you have seen a galvanometer in the galvanometer in the lab, as well as you have seen a voltmeter. Now, actually, you know, a galvanometer and a voltmeter, both the instruments are one and the same, with slight modifications in the galvanometer makes it a voltmeter. Now, when you are converting a galvanometer into a voltmeter, there are three main quantities or three main specifications are to be required. One is the voltage measuring capacity of the instrument has to be increased. Uh, See, when you are connecting a galvanometer in a circuit that is capable of detecting the presence of very small PD through the circuit, that means it has a voltage measuring capacity, very low measuring capacity it has got. So we have to, when we are converting that into a voltmeter for measuring only voltage or potential difference, you have to increase the voltage measuring capacity of the instrument. Then you know that a voltmeter, when it is measuring potential difference, you will be connecting a voltmeter always parallel to the circuit, so that it will be capable of measuring the potential difference across that two points over which it is connected. So the effective resistance of the voltmeter has to be very high, or in an ideal case the voltmeter should have infinite resistance. That means the effective resistance of galvanometer has to be increased in order to convert that into a voltmeter. And also, if a higher voltage is passing through the voltmeter, there are chances that the needle of the voltmeter may get bent due to the passage of higher potential difference. Therefore, the instrument has to be protected from higher flow of potential difference, or it has to be protected from damages causing to the instrument due to the flow of higher potential difference applied across it. So we can see that by connecting a very high resistance in series to the galvanometer, we can convert a galvanometer to a voltmeter. That is, connecting a very high resistance in series with the galvanometer, then that galvanometer is now converted into a voltmeter. Now we will try to find or how the series resistance can be calculated. Now, once you are measuring the potential difference across the resistor, you will be connecting this, that is the voltmeter, parallel to the resistance. This will measure the potential difference across the resistor. Now, you see this is the galvanometer, and this is the very high resistance, as I told you. Connecting a series resistance with the galvanometer will convert the galvanometer into a voltmeter. So this rectangular box now is a voltmeter, not a galvanometer. Now inside of the galvanometer, you have seen there is a rectangular coil and it is connected to a pointer. Now that coil will be connected to a series resistor, and then accordingly the deflection of the pointer will be marked in the indicator. Now this is a voltmeter now. Now you know the potential difference across the resistor is equal to V, which is equal to the potential drop across G plus the potential difference across X. So you can see V is equal to Ig into X. plus Ig into G. So the potential fall across the resistor will be equal to Ig into X plus Ig into G, or we are trying to find out the value of X. So we are shifting X to the left hand side and we get the expression X into Ig is equal to V minus Ig into G. And solving this, the final expression for the resistance is given by X is equal to V divided by Ig minus G. Now, you know that when a current Ig is flowing through this galvanometer, it will give full scale deflection to the galvanometer. So, if we want to increase the range of the voltmeter, that is, when we are converting a galvanometer into a voltmeter, the voltage measuring capacity is increased. So we are increasing the voltage measuring capacity of this voltmeter by n times. So N will be equal to V divided by Vg. What is this Vg? Vg is the potential difference for which the voltmeter initially was showing full scale deflection, and now we want to measure that voltmeter. The voltage that the voltmeter will be measuring is increased to V, which is N times Vg. So we are representing it as NV with a subscript V, which is, just for you to understand, it is it is representing corresponding to the voltmeter, not for the current. There we simply use the term N for N times I. G is equal to I. That was the expression we used in the case of conversion into an ammeter. So in this slide we are finding out the value of the potential to be measured is NV times the potential drop, which gives the full scale deflection, that is Vg. So NV times Vg is equal to V. Or what is Vg? Vg is the potential fall across the galvanometer, that is Ig into G. Substituting that and substituting in this expression, the value of V is substituted. So you will get V is equal to NV times Vg. So NV into Vg minus Ig into G. Simply substituting in this expression and solving this, you are substituting Vg by Ig minus Ig into G divided by Ig. Here what we have done, we have kept only X on the left hand side and we have taken Ig to the right hand side. Now substituting the potential drop across Vg, that is across the galvanometer, as Ig into G, we will get the term NV IgG divided by G minus Ig into G divided by G. You can see the common term here, Ig on numerator as well as denominator. Here also numerator and denominator. That term gets cancelled and the final expression will be X is equal to G into NV minus 1. You get this expression for the series resistance to be connected in series with the galvanometer to convert that galvanometer into a voltmeter whose current voltage carrying capacity is increased NV times. So that is the expression. Now we will proceed towards a problem based on what we have understood now. Now the question you can read here, galvanometer has a resistance of 25 ohms and its full scale current, deflection current is 25 microamperes. That means Ig is 25 microamperes. And what resistance should be added to have a range of 0 to 10 volt? That is, this galvanometer will give a full scale deflection for a current of 25 microampere and the galvanometer is having a resistance of 25 ohms. So you know the potential fall across G will be 25 into 25 microamperes. So it has to be converted into amperes. So the fall of potential, that is Vg, will be Ig into G. So we will try to solve the problem using this formula. X is equal to V divided by Ig minus G. And here Vg is not given. Even though we can calculate Vg, we can even, because the given quantities are Ig is given, V is given and G is given. So you will get the value of X is equal to, substituting the value of V, that is the maximum voltage that we want to measure, that is 10 volt, divided by 25 into 10 to the power minus 6 minus the value of G, that is 25. So solving this expression, we get the final answer to be equal to 399.975 into 10 to the power 3 ohms. So this resistance, when we connect in series with the galvanometer, this becomes a voltmeter which measures a voltage up to 10 volt. Now we will shift to the next slide, where we are solving another sum using both the finding the current as well as the converting it into a voltmeter as well as a ammeter. So here the question reads like this: a galvanometer has a resistance of 40 ohm and its full scale deflection current is 4 milliamperes. What is the resistance and how it is to be connected to convert the galvanometer into an ammeter whose range is 0.4 ampere, and it is converted into a voltmeter whose range is 0.5 volt. Now I hope you understood the question. The question is, this galvanometer is having a resistance of 40 ohm, or you can write G is equal to 40 ohm, and Ig, the current that gives full scale deflection, is 4 milliampere. Now we have to increase the ammeter range to 0.4 amperes. So we have to connect a shunt resistance parallel to the galvanometer in order to convert this galvanometer to read a maximum current of 0.4 ampere. So we will see the equation: I minus Ig into S is equal to Ig into G, that is potential across this must be equal to the potential across S. That was the basic thing in the conversion of a galvanometer to a voltmeter, to an ammeter. So it will be I minus Ig into S is equal to Ig into G. So solving that, you will get, we are given the value of Ig, you know the value of I, that is 0.4 ampere, and you know the value of capital G. So substituting the values, you will get the expression Ig divided by I minus Ig into G, which is equal to this, and the final expression will be 0.16 divided by 0.396, which is equal to 0.4040 ohms. Now this resistance, the question it is asked how this resistance has to be connected. Now you know that when we are converting a galvanometer into an ammeter, we have to connect this shunt resistance, that is that small resistance, in parallel to the galvanometer. So you can see this resistance should be, that S will be 0.4040, which is connected parallel to the galvanometers. This forms the final answer for the question A. Now we will proceed towards the B part of the question, and there we know value of Ig is given, value of G is given, we know the value of V also, that is 0.5 volt. So we can find out the value of X using this expression. So we can substitute the value of V, Ig and G, and solving that you get the answer as 85 ohm. Now how this 85 ohm has to be connected? Because we are converting the galvanometer into a voltmeter. So we have to connect this 85 ohm resistance to be connected in series to the galvanometer. So that will form the final answer for the V part. Here we are connecting this 85 ohms in series to the galvanometer so that it will be converted into a voltmeter whose range is equal to 0.5 volt. We will see, we have already explained about ammeter as well as we have completed the explanation of voltmeter. Now we will try to compare what is an ammeter and what is a voltmeter. What are the differences? We will just see what are the comparison quantities. That first thing, what this ammeter is used for? Ammeter is used for measuring the current. So the first point that you will write is that is an ammeter is used for measuring current. And the point corresponding to that in the case of voltmeter is a voltmeter measures potential difference. So it is used for measuring potential difference. That is the first point. Now, when you are converting an galvanometer into an ammeter, you will be connecting a very low resistance in series, or it is connected, low resistance is connected in parallel to the galvanometer. So that is the second point. Now, when you are converting this galvanometer into a voltmeter, we are connecting a very high resistance in series to the galvanometer. Now, when you are measuring the current, the ammeter is connected in series in the circuit and the voltmeter is connected parallel to the circuit, parallel to the point where we are measuring the potential difference. Now the next point, suppose we are connecting a smaller shunt, the current that can be measured will be accordingly more, and here in the case of voltmeter, greater will be the resistance that you are connecting, that is the value of X is high. The potential difference that you can measure with that will be accordingly very high. And the last point is the resistance of the ammeter is equal to, here you know the galvanometer resistance is G, the shunt resistance is S. So using that you will get the calculation, that is two resistances connected in parallel. In 11th standard you have studied how to calculate the effective resistance of two resistances connected in parallel, which is if R1 and R2 are connected in parallel, what is the effective resistance? It is given by R1 R2 divided by R1 plus R2. So here we have got two resistances G and S connected parallel. So the effective resistance is SG divided by S plus G, which is equal to G divided by N. Now corresponding here, we have got the resistance of the voltmeter, which is G and X connected in series. That is two resistances connected in series. What is the effective resistance? R1 and R2 connected in series. So the effective resistance is equal to R1 plus R2. So you will get G and X connected in series. So the effective resistance is equal to G plus X, which is also equal to G times NV. What is this? NV is the order in which it is increased. The voltage measuring capacity is increased by NV. So you can, these are the comparing terms of a ammeter and a voltmeter. Now the last topic is about thermoelectricity. It is found that when a current is passing through a resistor, you know that some electric current is generated. The reverse effect, that is, if due to the presence of thermal energy, is it possible to produce electric current? This was discovered by Seebeck, and the effect of producing electric current due to thermal energy is called thermoelectric effect. This is called thermoelectric effect, and it is also called as Seebeck effect. Now, when you are connecting two dissimilar metals, to form two joints will be formed when you are joining two dissimilar metals to form two junctions, and if one junction is heated and the other junction is cooled, you will get two junctions, one is hot and the other is cold. And it is found that a current is or a small EMF is generated which will allow a small current to flow through the metals that are joined together. And the small EMF that is generated is called thermo EMF, and these two dissimilar metals joined together to form two junctions is called a thermocouple. And the EMF that is generated due to heating of one junction and cooling of the other junction, that is called thermo EMF. Now here in the diagram you can see there is a thermocouple formed by two metals, that is antimony and bismuth. We are getting two junctions, and this is called an antimony bismuth thermocouple. And the current direction, you can see it is from antimony to bismuth at the cold junction. In order to remember this, you can just remember ABC, from antimony to bismuth at the cold junction. And you can see another example of a thermocouple, that is iron and copper. Metal wires are joined together, iron and copper joined together to form two junctions, and the one junction is heated and the other junction is cooled. And you can see the current is flowing from iron to copper at the cold junction, or you can say copper to iron at the hot junction. And this effect is reversible. I mean to say that if I am changing the junctions that are heated and cooled, that is, if I change this junction, that is, the left hand side junction is cooled and the right hand junction is heated, that means the direction of current will also get reversed. So you can see thermoelectric effect is a reversible effect, and this was discovered by Seebeck, and it is a reversible process. So you can see with this we are ending the discussion of current electricity chapter, and thank you so much, and drop all your doubts in the comment section. So we will stop here.